Okay. Assalamualaikum warahmatullahi wabarakatuh. Praise be to God, the most gracious and merciful. Good afternoon, everyone.
Afternoon.
The Honorable the Director of the Postgraduate Studies of UNTIRTA, Dr. Aan Aspianto, the Honorable the Head of the Master Program of Math Education of UNTIRTA, Dr. Hapsi Nindiasari, and the Head of International Office of UNTIRTA, Hudi Samanhudi PhD, and the speaker of this visiting scholar program, Dr. Cheng Meng. So, how are you today?
Thank you.
It's an honor for me to be your moderator.
Thank you.
And I am welcoming all of you to the Visiting Scholar programs held in collaborations of International Office of UNTIRTA and the Master Program of Math Educations of UNTIRTA. In this event, Dr. Cheng Meng will present a topic on cognitive diagnostic assessments of primary pupils' learning of time. For your information, this event is being attended by participants from various academic institutions in Indonesia, such as Universitas Negeri Yogyakarta, Universitas Negeri Jakarta, Universitas Negeri Malang, and some are also from Riau Province and Gorontalo, far away in Sulawesi, and also some are from Palembang. I am Dina Rahmawati. I will be the master of ceremony and also the moderator of this program. So I am a full package. I am replacing actually, by the way, Bapak Dr. Cecep because he has an urgent business in Jakarta today. Before proceeding to the presentation sessions, I would like to read the rundown of this program. This is the opening, okay. And second is the opening speeches from the Director of Postgraduate Studies and the Head of Master Program of Math Education. And the third is presentations from Dr. Chu, and you have around 45 to 60 minutes of presentations. And fourth is the Q&A sessions. And the last is closing, and going to the next agenda is the opening speech from Dr. Aan Aspianto. Bapak Dr. Aan Aspianto. Okay, Bapak Dr. Aan Aspianto.
Okay, thank you very much.
Okay, thank you very much, sir. Okay.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wa syukurillah wa la hawla wa la quwata illa billah. Rabbi shrah li sadri wa yassir li amri.
Udah dimulai.
Wahlul
Ini,
uqdatan
ini udah opening speech.
Distinguished Profesor Dr. Haji Insinyur Fatah Sulaiman STMP, Profesor Sultan Ageng Tirtayasa University, distinguished keynote speaker Dr. Cheng Meng from Universiti Sains Malaysia, distinguished guests, distinguished ladies and gentlemen. Izinkan saya untuk menyampaikan kali ini sambutan dalam bahasa Indonesia. Mohon maaf Bapak Dr. Cheng Meng, karena yang terhormat Bapak Dr. Cheng Meng ini orang Melayu, ya, orang Malaysia. Ya. Izinkan kali ini biasanya dengan Dr. Dina saya menyampaikan dalam bahasa Inggris. Ya, ya Bu Dina. Yang saya hormati Bapak Rektor Universitas Sultan Ageng Tirtayasa yang saat ini sedang sakit karena terpapar COVID-19 dan 14 hari ke depan beliau tidak bisa hadir di kampus. Mohon doanya dari seluruh hadirin dan hadirat untuk mendoakan semoga beliau diberikan kesembuhan dengan segera. Yang saya hormati Wakil Direktur 1 Profesor Kartina, Wakil Direktur 2 Dr. Helmi, dan Wakil Direktur 3 Profesor Alfirano. Spesial yang kami hormati, yang kami muliakan, keynote speaker Bapak Dr. Cheng Meng. Terima kasih atas kesediaan Bapak untuk hadir di webinar ini. Yang kami hormati Ibu Dr. Hepsi Nindya Sari, MPD, Kaprodi S2 Matematik dan dari Pasca Sarjana Untirta, Ketua Pusat Pelayanan Internasional, Dr. Udi Samanhudi yang sekarang diwakili oleh Dr. Dina Rahmawati, yang sekaligus sebagai moderator. Yang saya hormati Koordinator Program Doktor S3, beserta seluruh jajaran dan dosennya, juga yang saya hormati seluruh Kaprodi dan Sekprodi, beserta seluruh dosennya. Wabil khusus yang kami hormati dosen-dosen sebagai peserta dari Riau, dari Palembang, dari Malang, dari pulau-pulau yang lain, yang seluruh Indonesia yang saat ini mudah-mudahan bergabung mencapai 300. Yang saya banggakan, para mahasiswa yang ikut webinar ini dalam acara, dalam kegiatan International Visiting Scholar Program Masters of Mathematics Education Program Graduate School Untirta dengan tema Cognitive Diagnostic Assessment of Primary Pupils Learning of Time. Bapak-bapak, ibu-ibu yang saya hormati, seluruh peserta webinar dari Sabang sampai Merauke, wabil khusus Bapak Dr. Cheng Meng. Izinkan saya untuk menyampaikan sekilas berkaitan dengan tema penilaian diagnostik kognitif dasar terhadap waktu belajar siswa. Kebetulan latar belakang saya adalah hukum pidana. Pak Doktor, ya mohon kiranya saya hanya sedikit saja mengulas bahwa asesmen diagnostik kognitif ini di mana asesmen diagnostik dapat dilakukan secara rutin. Yaitu ketika pengajar akan memperkenalkan topik pembelajaran baru, juga pada akhir ketika pengajar sudah selesai menjelaskan dan membahas sebuah topik. Juga di waktu yang lain selama semester berlangsung. Tentunya tujuannya adalah untuk mendiagnostik kemampuan dasar peserta didik dalam topik sebuah mata pelajaran. Asesmen diagnosis dapat mengandung satu atau lebih dari satu topik. Misalnya, asesmen diagnosis untuk matematik bisa juga mengandung topik integral atau semua topik dalam matematik. Umpamanya integral, diferensial, interpolasi, dan lain-lain. Kebetulan saya juga, Pak Dr. C, saya ini S1-nya dari statistik juga dari matematik ya. Kebetulan saya sekarang karena kuliah lagi, kuliah hukum, S1, S2, S3-nya, jadi saya pernah jadi dekan Fakultas Hukum juga. Jadi saya pernah mengenal matematik, Pak Dokter ya. Nah, itu mungkin secara deskriptif, asesmen diagnosis ini dapat memetakan kemampuan semua siswa di kelas secara cepat untuk mengetahui siapa saja yang sudah paham, yang agak paham, yang belum paham, sampai pengajar dapat menyelesaikan materi sesuai dengan kemampuan siswanya tersebut. Yang saya tahu dari literatur yang berhubungan dengan domain tujuan pembelajaran. Salah satunya adalah tujuan belajar dinamai taksonomi mencakup 3 domain, kognitif, afektif, dan psikomotorik. Di mana kognitif itu mencakup 6 perilaku khusus yang tersusun dari yang terendah sampai yang tertinggi, seperti knowledge, comprehension, application, analysis, synthesis, evaluation, sedangkan afektif itu juga berkaitan dengan kesadaran yang berasal dari individu untuk menggunakan atau menerima sikap, prinsip, kode, dan sanksi yang mendukung keputusan nilai dan mengarahkan pelakunya tersebut. Perilakunya tersebut. Sedangkan domain afektif itu beberapa tahap. Ada penerimaan, ada menanggap, ada menilai, ada mengorganisasikan nilai, karakteristik nilai, atau characterization by value or value complex. Yang terakhir itu domain psikomotorik yang menekankan pada perilaku yang mencakup gerak tubuh, koordinasi gerak, komunikasi nonverbal, dan perilaku bicara. Ada hal-hal lain yang nanti akan dibahas oleh keynote speaker yang tentunya ini sangat bermanfaat bagi kita semua, baik dosen, guru, bahkan mahasiswa kita yang mengikuti perkembangan dari webinar ini. Dengan demikian, para pengajar hendaknya mampu mengantisipasi aspek-aspek perubahan perilaku, mulai dari perencanaan kegiatan mengajar, menumbuhkannya dalam pelaksanaan kegiatan belajar mengajar, dan juga harus memahaminya. Perlu diingat bahwa perilaku belajar bisa bersumber dari berbagai aspek perilaku lain. Itu sudah kita ketahui, baik yang bersifat internal maupun yang bersifat eksternal. Di antara aspek internal ini bisa dipahami seperti potensi, prestasi, kebutuhan, minat, sikap, pengalaman, kebiasaan, emosi, motivasi, kepribadian, perkembangan, keadaan fisik, cita-cita, dan lain-lain. Hadirin peserta webinar yang saya hormati, perilaku belajar yang efektif disertai proses belajar yang tepat diharapkan mampu menghasilkan manusia-manusia yang memiliki karakteristik pribadi yang mandiri, siswa yang efektif, pekerja yang produktif. Pribadi yang mandiri itu adalah pribadi yang mampu mengenal dan menerima dirinya sendiri dan lingkungannya. Mampu mengarahkan dirinya dan pada gilirannya dapat mewujudkan dirinya secara optimal. Demikian kiranya yang dapat saya sampaikan. Sekian sambutan dari saya. Terima kasih atas perhatian. Semoga kiranya webinar ini dapat berlangsung dengan baik dan lancar. Thank you very much. Wallahu muwaffiq ila aqwamit thoriq, billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the opening speech from Dr. Aan Aspianto. Now coming to the opening speech from the head of Math Education Program, Ibu Hapsi.
Thank you very much, Ms. Dina. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang dan selamat buat kita semua. Yang saya hormati Bapak Rektor Universitas Sultan Ageng Tirtayasa, Profesor Haji Dr. Fattah Sulaiman. Yang saya hormati Bapak Direktur Pasca Sarjana Dr. Haji Aan Aspianto, SSI SHMH. Yang saya hormati Bapak Ibu Wadir 1, Wadir 2, dan Wadir 3. Dan khususon saya hormati narasumber kita, Mr. Dr. Cheng Meng from Universiti Sains Malaysia. Thank you very much, Mr. Dan juga yang saya hormati Bapak Ibu Kaprodi S1, S2, dan S3, serta Sekprodi di kalangan Pasca Sarjana Universitas Sultan Ageng Tirtayasa, serta para peserta webinar pada siang hari ini yang saya banggakan. Alhamdulillahirrahmanirrahim, puji syukur kehadirat Allah Subhanahu wa Ta'ala, kita masih diberikan nikmat sehat, nikmat luar biasa semangat untuk mengikuti kegiatan webinar kami pada siang hari ini dalam program International Visiting Scholar Program Master of Mathematics Education Program Graded School UNTIRTA. Bapak Ibu sekalian yang saya hormati, saya ucapkan juga banyak terima kasih kepada Bapak Dr. Aan Aspianto dan juga Bapak Dr. Udi Samanhudi selaku Ketua Pelayanan Internasional Office UNTIRTA yang sehingga pada siang hari ini kegiatan webinar kita bisa berjalan dengan baik. Dan juga saya ucapkan banyak terima kasih untuk Mr. Dr. Cheng Meng. Thank you very much for your time as speaker in our webinar, Mr. We meet again before we will go to University Sains. Thank you very much.
Yeah.
Bapak Ibu sekalian yang saya hormati, kegiatan kita pada siang hari ini yaitu mengangkat tema Cognitive Diagnostic Assessment of Primary Pupils Learning of Time, di mana kita tahu sebagai seorang pendidik, baik sebagai guru, kemudian sebagai dosen maupun calon guru, kegiatan asesmen ini adalah sangat diperlukan sebagai kewajiban kita untuk melaksanakan dalam proses pembelajaran. Terlebih dalam kegiatan kurikulum 2013 yang mengharuskan kita untuk melakukan penilaian otentik, penilaian yang tidak hanya kita lihat dari hasil belajarnya saja, tetapi dari awal dan juga proses pembelajarannya. Di mana kompetensi yang kita akan nilai ini tidak hanya secara kognitif juga, tetapi juga secara afektif dan juga secara psikomotorik. Dan untuk webinar kali ini, Pak Dr. Cheng Meng akan mengangkat terkait dengan diagnostik dalam hal kompetensi kognitif, asesmennya. Mudah-mudahan ini bisa menjadi bahan masukan buat kita, sehingga peningkatan hasil belajar anak-anak kita bisa lebih baik lagi. Bapak Ibu sekalian yang saya hormati, kita tahu bahwa siswa SD adalah siswa yang juga perlu sangat diperhatikan dalam kompetensi dasar matematik, mengingat kita tahu bahwa matematik adalah ilmu terstruktur yang satu sama lain saling terkait. Kalau andaikan membangun sebuah gedung, maka gedung itu akan runtuh jika fondasi matematiknya tidak kuat. Dengan demikian, mudah-mudahan dengan pemaparan dari narasumber kita pada siang hari ini, kita bisa mampu bagaimana mendiagnostik secara cepat asesmen kognitif anak-anak kita, sehingga kita segera bisa memberikan umpan balik, memberikan tindakan selanjutnya untuk meningkatkan proses belajar dan juga hasil belajar anak-anak kita. Bapak Ibu sekalian yang saya hormati, saya ucapkan banyak-banyak terima kasih atas peran sertanya pada kegiatan webinar pada siang hari ini, dan juga semoga Bapak Ibu mendapatkan ilmu yang bermanfaat dan keberkahan dari kegiatan hari ini. Bapak Ibu sekalian yang saya hormati, saya ucapkan selamat mengikuti webinar. Mohon maaf jika ada hal-hal yang tidak berkenan pada kegiatan siang hari ini. Saya akhiri, wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Ibu Dr. Hapsin Indiasari, for the speech. Before coming to the main sessions, I would like to firstly, I'll shortly read the curriculum vitae of our main speaker of this webinar. Okay, Dr. Chu is an associate professor. He obtained his PhD in mathematics education from University of Malaysia, Kuala Lumpur in 2007, and currently he's a senior mathematics education lecturer at Universiti Sains Malaysia, Penang. He's the course coordinator of mathematics teaching methods and also coordinator of statistical reasoning and educations. His research interest is teaching and learning in mathematics using the geometrist sketchpad, Van Hele theory of geometric thinking and lesson study. Okay, without any further ado, but before that, for the participants, you can post questions in the chat box, or you can later ask the questions directly to Dr. Chu. Okay, Dr. Chu, the screen is yours.
All right, thank you very much, Dina. Can I share my screen now?
Yeah, please.
Okay, can everyone see my screen?
Yeah.
All right, okay. So allow me to speak English, and first and foremost, I'd like to express my sincere thanks to Dr. H. Hasbianto, the Director of Graduate School, Universitas Sultan Ageng Tirtayasa or UNTIRTA, Dr. Hapsin Indiasari, Head of Masters of Mathematics Education Program of Graduate School UNTIRTA, Dr. Dina Ratnawati, the moderator of today's program, and Dr. Udi Samanhudi, Head of International Office UNTIRTA, for inviting me as the speaker of today's International Visiting Scholar Program. And a very good afternoon to my respected lecturers and students, and ladies and gentlemen. The title of my presentation is Cognitive Diagnostic Assessment of Primary Pupils' Learning of Time. And in this presentation, I'm going to share with you first the background to study, then what is cognitive diagnostic assessment of CDA. This is followed by strengths of CDA, why focus on the topic of time, objectives of the study, theoretical framework of the study, methodology, development evaluation of CDA, an example of score profile, and finally, conclusion. Background of the study, according to Buhaya from University of Malta, in his article, he argued that the traditional forms of assessment, namely tests and examinations, are unfriendly in four main aspects. Okay. First, learning unfriendly. Second, curriculum unfriendly. Third, teacher unfriendly. And fourth, student unfriendly. Traditional tests and examinations are learning unfriendly because A, they may reveal what students remember about what teachers think they should remember, but do not help teachers to get the truth, meaning, purpose, or utility. B, they basically represent a narrow form of assessment, that is, they only assess a very narrow range of academic qualities. C, they represent a sudden death form of assessment, that is, students get credit only for what they do during the brief test or examination period. And D, they represent an uninformative form of assessment, that is, the test or examination grade does not define what a student really knows and can do. Second, traditional tests and examinations are curriculum unfriendly because A, they emphasize recall of factual knowledge with a heavy reliance on memory and rote learning. B, they can lead teachers to coach their students in a narrow range of test-taking skills rather than encourage them to teach a broader range of higher-order competencies and understandings. And as a result, students develop problem-solving strategies that help them pass tests or examination without reaching the intended learning goals. And third, traditional tests and examinations are teacher unfriendly because the knowledge that tests and examination scores are the sole means of describing and judging schools produces in teachers the determination to do what is necessary to produce students with high scores, and teachers will teach to the test. That is, they teach students only what is necessary in order to pass a particular test or examination, rather than help them develop a range of competencies. And this translates itself in the test-like teaching program to avoid being publicly embarrassed and humiliated. And many teachers may, in fact, even be willing to engage in questionable, educationally indefensible practices to increase their students' test or examination scores. And as a result, the purpose of assessment becomes merely for improving the scores and not understanding pupils' learning process. And finally, traditional tests and examinations are student unfriendly because tests and exam scores are used to label students as good or weak students without providing meaningful interpretation of their learning progress. And B, however, teachers require meaningful feedback about their students, such as their cognitive strengths and weaknesses, in order to help them learn effectively. And without this fine-grained information, teachers will not be able to understand their students' learning process. And thus, traditional forms of assessment, instead of motivating all students to work harder and encouraging them to carry on learning, have a demotivating influence on most of them and effectively pushes them out of the system. In addition, there's a phenomenon of overemphasizing students' achievement in centralized national examinations or high-stakes examinations in the education system of many countries. For example, Malaysia is one of the countries that implements the centralized national examination system. And in this system, the focus of the stakeholders, such as school administrators, teachers, parents, as well as media, is on students' performance in the national examinations, such as publicizing the number of A's attained by the students. This type of examination system is unfriendly because it is unable to provide an accurate result of a particular student's real competencies, and it might put pressure on teachers to produce high-score performers in the assessments. Therefore, there is an urgent need to provide each pupil with a detailed score profile, such as those generated by cognitive diagnostic assessment, which shows the mastery level of each of the tested attributes and provide feedback to the relevant stakeholders. And what is cognitive diagnostic assessment? CDA. CDA is a relatively new diagnostic assessment method which provides meaningful feedback on the cognitive strengths and weaknesses of an individual examinee. CDA uses a cognitively grounded approach, that means based on expert-based cognitive models, with items designed to diagnose pupils' specific knowledge structures and processing skills for a particular topic, such as the topic of time in this study. And the result of CDA, expressed in the form of knowledge state, provides a detailed diagnostic information about a learner's learning process in terms of mastery or non-mastery of a particular attribute. An attribute refers to the knowledge or skills that are needed to correctly solve a given task or item. Knowledge state is a systematic way of expressing the attribute mastery level of a test taker in the respective tested domain. And more importantly, knowledge state shows the patterns of attribute mastery and informs pupils of their cognitive strengths and weaknesses. Therefore, CDA is very much needed in current educational context because analyzing an examinee's score profile, which shows the performance on the assessment items and knowledge state, is more meaningful than just obtaining a total score. For example, pupils who have the same score may show different performance on the CDA items and knowledge states. As shown in the table, pupil A and pupil B have the same total score of 9 because they correctly answered 9 items out of the 18 items in the CDA. But pupil A and pupil B showed different performance on the CDA items and knowledge states. That is, pupil A correctly answered items 1, 2, 3, 4, 5, 6, 7, 8, and 9, and showed a knowledge state of 1, 1, 1, 0, 0, 0. Whereas pupil B correctly answered items 1, 2, 3, 4, 5, 6, 7, 8, and 10, and showed a knowledge state of 1, 1, half, 0, 0, 0. Pupil A's knowledge state of 1, 1, 1, 0, 0, 0 indicates that pupil A showed mastery of attributes A1, A2, and A3, but non-mastery of attributes A4 and A5 and A6. While pupil B's knowledge state of 1, 1, half, 0, 0, 0 indicates that pupil B showed mastery of attributes A1 and A2, inconsistent mastery of A3, but non-mastery of attributes A4 and A5, A6. As highlighted by Alderson, Clapham, and Wong, that individuals may reach the same overall score in a variety of different ways and thus be awarded a pass, although their profiles are different. This is one of the main reasons why profiling of test results is considered by many to be superior to reporting one overall result, whether it is a pass or fail result or a score to be interpreted by test users. Indeed, score profile plays an important role as a platform of communication between the test developer and the test users. The score profile generated from CDA is able to provide diagnostic feedback that is descriptive and easily interpreted. And this kind of comprehensive diagnostic information allows the learners to remedy themselves while the teachers can use it to improve their teaching. And according to ALF 2012, CDA as an educational assessment has 4 main strengths. First, CDA can be used for both summative and formative purposes. That is, it can be used at the end of an academic year to capture the overall learning outcomes of the pupils throughout the year. It can also be used as formative assessment to identify the knowledge and skills that are still required to be emphasized in the next instructional planning. Therefore, it provides a comprehensive feedback for teachers to make effective instructional decisions. Second, CDA provides a detailed score profile of pupils' performance, and this profile shows the pupil's mastery level of each of the attributes that was measured by the CDA. And based on the score profile, the pupil will have a clearer picture of his or her level of mastery of the attributes. And the score profile generated from CDA is also known as the cognitive profile. And third, CDA can be used by teachers to monitor and understand their pupils' learning progress and knowledge state. Therefore, CDA can help teachers to design remedial instruction for improving their pupils' learning progress and knowledge state. And finally, the feedback provided by CDA is constructive in nature to both stakeholders and pupils, as it depicts not only the cognitive strengths of the pupils, but also shows the areas for improvement. As a result, this fine-grained information can help motivate pupils to put in more effective actions towards achieving the learning outcomes. And why focus on the topic of time in this research? The reason is time is a basic concept used in everyday life. Since we wake up in the morning till we sleep at night, our life revolves around the concept of time. Many children start to learn about the concept of time since preschool. Yet, time is a complex and abstract concept. In fact, many primary school teachers highlighted that their pupils have difficulty in understanding the concept of time. And Lim, Xia, and Tan 2020 show that many pupils are particularly weak in the calculation of duration and conversion of units of time. And research has shown that time is an abstract concept, which is not easy to teach to children. According to McGuire, time does not easily link with the other topics of measurement due to its abstract nature. That is, you can't go into a shop and buy a dozen minutes. Hence, time is a problematic learning content area for primary pupils. In the Malaysian mathematics syllabus, the topic of time is taught in preschool and primary school and is briefly covered in secondary 1 or grade 7. This implies that pupils do not have the opportunity to master the knowledge and skills in the topic of time after secondary 1. Therefore, it's very important that primary pupils should master the knowledge and skills in the topic of time before they leave primary school. In addition, poor mastery of the knowledge and skills in the topic of time might influence students' learning in other subjects too, because time is integrated in several subjects such as history, example, chronology, geography, example, deep time, and literacy, example, time-related vocabulary. Since time is an essential part of our basic knowledge in daily life, teachers should apply appropriate methods to teach the topic of time and at the same time identify pupils' difficulties in acquiring the concept of time. Yet Bernie highlighted that despite the fact that authors continuously point at the complexity of time conceptions and the difficulties involved for children, the available research does hardly to understand what makes time so complex for children to grasp. Therefore, it's crucial for teachers to employ an appropriate assessment to identify pupils' cognitive strengths and weaknesses in the topic of time. As such, this study was carried out to develop an appropriate assessment called CDA that can diagnose primary pupils' learning of the topic of time. Specifically, the objectives of the study were: 1, to develop a CDA of primary pupils' learning of the topic of time. 2nd, to determine whether the attributes in the expert-based cognitive models are arranged hierarchically based on pupils' responses. And 3, to determine the consistency or model data fit between the expert-based cognitive models and pupil-based cognitive models. The assessment triangle theory was the underlying theory used to develop and evaluate the CDA in this study. The assessment triangle theory was, based on the theory, there are 3 vertices in the assessment triangle. That is the cognition, observation, and interpretation vertices, as shown in figure 1. As shown in the figure, the cognition vertex is represented by the cognitive model constructed according to the cognitive component of the attribute hierarchy method, or AHM. And the observation vertex is represented by the diagnostic tasks or items of CDA, and the interpretation vertex is represented by the psychometric component of AHM. And the 3 vertices, the cognition, observation, and interpretation vertices, are interconnected and work as a whole to obtain meaningful inferences from the CDA. The attribute hierarchy method, or AHM, is a relatively new psychometric procedure used to classify examinees' item response patterns into a structured and expected response patterns, which will be generated based on the cognitive model. And the important assumption of AHM is that test performance depends on the set of hierarchically arranged attributes called attribute hierarchy. And this assumption is made based on the premise that cognitive skills are all interrelated and connected through a network. The attribute hierarchy plays an important role in AHM because it's the basis for an accurate diagnostic inference. In order to form an attribute hierarchy, attributes need to be arranged sequentially from the easiest to the most difficult. For example, a pupil must have the knowledge of 1 hour equals 60 minutes before he or she is able to convert 3 hours into 180 minutes. In this case, the attribute of knowing 1 hour equals 60 minutes is a prerequisite attribute for converting 3 hours into 180 minutes. And based on the attribute hierarchy in AHM, teachers will then have a better understanding of their pupils' learning process, which in turn will help them to design a more effective lesson. AHM consists of a cognitive component and a psychometric component. The cognitive component comprises the expert-based cognitive models for the development of the CDA items, whereas the psychometric component comprises the statistical analysis, such as HCI, Hierarchical Consistency Index, and attribute probability, or AP, of the data collected from the CDA. And to develop the CDA in this study, a set of defined attributes in the topic of time was first identified at the cognition vertex. Attributes, remember, are knowledge of skills needed to solve a given task or item. As AHM assumes that the test performance depends on the set of hierarchically arranged attributes, all the attributes were arranged hierarchically to form an expert-based cognitive model in the cognition vertex. An expert-based cognitive model displays an array of relationships between all attributes, which provides a basis for the development of diagnostic tasks. And at the observation vertex, the diagnostic tasks were designed based on the expert-based cognitive models in the cognition vertex to measure the intended attributes precisely so that diagnostic inferences can be obtained based on pupils' responses. Since the attributes are arranged hierarchically in the expert-based cognitive models, the complexity of diagnostic tasks also increases from the easiest to the most difficult. And this arrangement allows pupils' level of mastery of attributes in each expert-based cognitive model to be observed through their responses. And the data collected from the observations were analyzed by using the psychometric component of AHM at the interpretation vertex. With the application of AHM, the interpretation of a pupil's mastery of attributes was done by calculating the probability of a pupil mastering a particular attribute. And this attribute probability, or AP, shows a pupil's mastery level of each attribute. As a result, the pupil score profile, which shows the knowledge state, can be identified and thus serves the diagnostic purpose of the CDA. In addition, the hierarchical consistency index, or HCI, is used to determine the consistency or recall model data fit between the expert-based cognitive models and the pupil-based cognitive models. And this psychometric analysis provides firm evidence based on the observations made from the responses, and with this meaningful feedback about pupils' way of learning, as well as their cognitive strengths and weaknesses, can be obtained from the CDA. Methodology, this study employed a cross-sectional survey in which the data were collected from the selected pupils at a single point in time because it is effective for providing a snapshot of the current pupils' mastery of attributes in the population and has the advantage of providing the data relatively quickly. And cluster sampling was used to select 539 year 6 pupils from 3 types of average performing primary schools. That is 4 national schools or Sekolah Kebangsaan (SK), 3 Chinese national type schools or Sekolah Jenis Kebangsaan Cina (SJKC), and 4 Tamil national type schools, Sekolah Jenis Kebangsaan Tamil or SJKT in Penang, Malaysia. And all year 6 pupils in the selected schools were chosen as a sample of the study to make sure that year 6 pupils from a wide range of mathematics achievement were included in the study. Year 6 pupils were selected as a sample because they had completed the 6 years of primary mathematics education syllabus for the topic of time. And average performing primary schools were selected because the CDA developed in this study aimed to diagnose pupils' cognitive strengths and weaknesses in learning the topic of time. Therefore, pupils from high-performing schools were not selected because they might be able to answer all the items correctly, while pupils from low-performing schools were not selected because they might not be able to answer most of the items correctly. Thus, limited inferences could be made from their responses. The development and evaluation of CD in this study consisted of 2 phases. Phase 1 involved the development of expert-based cognitive models, while Phase 2 involved the generation of pupil-based cognitive models based on pupils' item responses. Phase 1 consisted of 3 steps. First, identification of attributes. 2, development of expert-based cognitive models. 3, item design based on the expert-based cognitive models, while Phase 2 consisted of 2 main steps. First, administering the CDA to the pupils and statistical analysis of the collected data. In step 1, mathematics examination questions from the past 5 years, 2009 to 2013, of the primary school evaluation test or Ujian Penilaian Sekolah Rendah (UPSR) were gathered, and questions related to the topic of time were sorted out by the researchers. UPSR mathematics questions were used because they assessed year 6 pupils' learning of the topic of time after they had undergone 6 years of primary mathematics education. In addition, the UPSR result also served as the benchmark for the primary pupils' performance to enter secondary school. Therefore, the use of UPSR mathematics questions was considered as appropriate in order to identify the important concepts and skills in the topic of time. And after checking through the 5 years of UPSR mathematics papers, 42 questions were found relevant to the topic of time. This set of questions was then given to the panel of experts to identify the questions that might be difficult for Year 6 pupils. The panel of experts comprised 7 excellent mathematics teachers in Malay, Guru Mathematics Cheng Meng, 3 from SK, 2 from SJKC, and 2 from SJKT. Excellent mathematics teacher, for information, is an award given by the Malaysian Ministry of Education to mathematics teachers based on their teaching experience and excellent performance. Selection of excellent mathematics teachers was just very important for this study because experts in primary mathematics education were needed in the development of the expert-based cognitive models of the study. In addition, the excellent mathematicians were assumed to know best their pupils' difficulties in learning the topic of time, and the panel of experts identified 11 questions from the set of 42 questions that might be difficult for Year 6 pupils. Then they tested these 11 questions on their Year 6 pupils, that is 10 Year 6 pupils on each type of primary school, 10 from SK, 10 from SJKC, and 10 from SJKT, so 30 pupils in all. The analysis of the pupils' responses showed that they were weak in duration and conversion of units of time. Next, based on the pupils' working steps in answering the questions, the panel of experts initially identified 11 main attributes as shown in Table 1. As shown in the table, the 11 attributes A1 to A11 were classified into 4 main categories: relationship, conversion, basic operation, and transformation. After several rounds of revisions, the panel of experts finally agreed on the 27 main attributes as shown in Table 2. And for information, several rounds of revisions took a lot of time. It's very time-consuming to come up with a set of attributes to form the expert-based cognitive models. So Table 2 shows 27 main attributes, final attributes. They were also classified into 4 categories, but with different names. The first category is relationship, basic operation, the second one. The third now is variables of duration, and the fourth one is transformation and reasonability of final answer. In addition, the main attributes in the last category, transformation and reasonability of final answer, were divided into 2 sub-attributes, such as A20A, A20B, A21A, A21B, and so on. This is because these attributes were involved in solving word problems. And as you know, to solve the word problems, pupils must be able to A, transform the text in the word problems into mathematical operations in order to solve the word problems. Then they must be able to present their final answer reasonably. For example, the final answer involving duration should be presented reasonably as 3 hours 40 minutes instead of 3:40 a.m. or 3:40 p.m. The validated list of attributes was then used for the development of the expert-based cognitive models in Step 2. So this is the end of Step 1, identification of attributes. Now we move on to Step 2, the development of the expert-based cognitive models. And based on the validated list of attributes, the panel of experts carefully examined the relationships among these attributes. The panel of experts then arranged these attributes hierarchically from the easiest to the most difficult attributes to form 8 attribute hierarchies or cognitive models. Attribute hierarchies are sometimes called cognitive models. These cognitive models are called the expert-based cognitive models because they were developed by the panel of experts. And figures 2A to 2H show the 8 expert-based cognitive models after several rounds of revisions. Figure 2A shows the first cognitive model, or CM1, for finding the end time of an event by addition of start time and duration involving minute and hour. So this attribute A1, attribute A4, A5, A14, A20A, A20B. So it consists of 6 attributes in the first cognitive model. This list of attributes I've shown you in the previous table, the 27 attributes. The last attribute is divided into 2 sub-attributes because it involves solving word problems, transform, and then give the answer reasonably. Okay, figure 2B shows the second cognitive model, CM2, for finding the duration of an event by subtraction of start time and end time. And figure 2C, cognitive model 3, finding the start time of an event by subtraction of end time and duration. This cognitive model was formed based on the easiest attribute, to the most difficult attribute following AHM, the attribute hierarchy method. And figure 2D shows the fourth cognitive model for finding the end time of an event by addition of start time and duration. And this is cognitive model 5, finding the duration of an event by subtraction of start time and end time. This is cognitive model 6, finding the start time of an event by subtraction of end time and duration. And 7 cognitive model, finding the total duration of 2 events. And finally, the 8 cognitive model, finding the difference between the duration of 2 events involving minute and second. So in step 3, so that was the end of step 2, development of expert-based cognitive models. And in step 3, the researchers developed the items based on each expert-based cognitive model, as well as primary textbooks and reference books. Step 3 is item design based on the expert-based cognitive model. So in this step, researchers developed the items based on the 8 expert-based cognitive models in step 2, and also reference books and mathematics textbooks. For example, an item to measure attribute A1 in CM1, cognitive model 1, knowing 1 hour equals 60 minutes would be 1 hour equals 60 minutes. And the difficulty level of each item increases as the attribute to be measured becomes more difficult, as arranged in each expert-based cognitive model that I showed you just now. And to increase, this is important, according to ALF 2012 and DROS 2011, to increase the reliability of the CDA, 3 parallel items, item salary, were developed based to measure each attribute in the expert-based cognitive models. For example, in CM1, the first cognitive model, attributes A4, A5, A14, A20A, and A20B were measured by 3 parallel items, that is 3, 4, and 5, 12, 13, and 14, 21, 22, and 23, and items 30, 31, 32, respectively, except for attribute A1. And in addition, increasing the number of items would reduce the probability of pupils correctly answering the items by guessing. So besides increasing the reliability, it can also reduce the chance of guessing by pupils, which might cause the results of the CDA to be unreliable. So the 3 parallel items, 3, 4, and 5, measured attribute A4. So these were the 3 items measuring attribute A4, item 3, item 4, and item 5. And the 3 parallel items, 12, 13, 14, measured attribute A5. And the 3 parallel items, 21, 22, and measured attribute A14. And finally, the 3 parallel items, 30, 31, 32, measured attributes A20A and A20B. A20A and A20B belongs to one main attribute. Remember, solving word problems. Attribute A1, attribute A1 in the first cognitive model, knowing 1 hour equals 60 minutes is the most basic attribute and could only be measured by one item. That is, 1 hour equals 60 minutes. So only one item measure A1. Whereas all the attributes were measured by 3 parallel items to increase the reliability of the CDA and also to decrease the chance of guessing by the pupils. And at the end of step 3, based on the 8 expert-based cognitive models, as well as primary mathematics textbooks and reference books, the researchers finally developed 75 items after several rounds of revisions. And the items were first developed in English, as it is the common language of the researchers and also the panel of experts. And the items were then translated into Malay, Mandarin, and Tamil languages to match the medium of instruction of SK, Malay School, SJKC, Chinese School, and SJKT, respectively. And this was to ensure that language would not be a barrier, would not be a hindrance for the pupils in answering the items. Then the panel of experts were invited to validate the items to ensure that they measured the attributes in the expert-based cognitive models. And the end of step 3 marked the completion of phase 1 in the development of evaluation of CDA. Now we move to phase 2. Phase 2 involved the generation of pupil-based cognitive models. And in step 4, administering CDA to the pupils, the validated items from phase 1 were administered to the selected sample of 539 year 6 pupils from 3 types of average performing primary schools, 4 national schools, 3 Chinese national type schools, and 4 Tamil national type schools in Penang. Altogether, there were 11 primary schools. After marking the answer scripts, only 505 complete answer scripts could be used for the statistical analysis in step 5. First, in step 5, statistical analysis of the collected now. First, the Cronbach's alpha was used to determine the reliability of the CDA. Table 3 shows the values of Cronbach's alpha for each cognitive model. As you can see in table 3, most of the values of Cronbach's alpha were above 0.70. And according to George and Mallory, 2003, a Cronbach's alpha value of more than 0.70 is considered as acceptable. So as shown in table 3, the Cronbach's alpha value for all the cognitive models were more than 0.70, indicating that the items in each cognitive model were at an acceptable level of reliability. Therefore, the first objective of the study, to develop a CDA of primary pupils' learning of the topic of science, had been achieved. Second, the attribute probability shows pupils' mastery level for each attribute. The values of attribute probability range from 0 to 1. For example, an attribute probability of 0.80 indicates that a pupil probably had mastered a particular attribute by 80%. Thus, the higher the value of attribute probability, the higher the probability that the pupil had mastered a particular attribute. The attribute probabilities are expected to decrease as attributes become more difficult in the attribute hierarchy or cognitive model. This is because pupils should have higher probability of mastering the easier attributes as compared to the more difficult attributes in the attribute hierarchy. An artificial neural network, or ANN, in MATLAB 2012 was used to obtain the attribute probability. We hired an expert in ANN to compute the attribute probability. And table 4 shows the mean attribute probability for each attribute in each cognitive model. As you can see, as shown in table 4, the mean attribute probabilities in 6 out of the 8 cognitive models, that is CM2, CM4, CM5, 6, 7, and 8, showed a decreasing pattern from the easiest to the most difficult attributes. For example, CM2, attribute A1, A9, A10 to A21B. This is the simplest, this is the most difficult. And you can see the mean attribute probabilities show a decreasing pattern. The values decreases from 0.96, 0.94, 0.85, 0.84, 0.82, and 0.74, right? And likewise, CM4, the mean attribute probabilities also showed a decreasing pattern. CM5, CM6, CM7, and CM8. Therefore, the attributes in the 6 cognitive models are arranged hierarchically based on the pupils' responses. That means the expert-based cognitive models can predict students' observed response patterns. The mean attribute probabilities in CM1 showed a decreasing pattern from the easiest to the most difficult attributes, except the mean attribute probability of A1 and A4. They are of the same values, right? 0.96, 0.96. Thus, the mean attribute probabilities in CM3 also showed a decreasing pattern from the easiest to the most difficult attributes, except the mean attribute probability for A10 and A16, 0.84 and then 0.86. So it shows an increasing pattern instead. Therefore, the conclusion, the attributes in the 2 cognitive models are not really arranged hierarchically based on the pupils' responses. In addition, the correlation coefficients, that means besides attribute probability, we need to analyze using correlation coefficient, whether the attributes were arranged hierarchically in the attribute hierarchy. So we calculated the correlation coefficients among attribute probabilities are expected to decrease as attributes become more difficult in the attribute hierarchy. This because the correlation coefficients among attribute probabilities are expected to decrease as the distance between the attributes in the attribute hierarchy increases. For example, A1 and A4, A1 and A20A, and the distance is not the same. So as the distance increases, we expect the correlation coefficient to decrease because they are further away in the attribute hierarchy. Table 5 to Table 12 show the correlation coefficients among attribute probabilities for CM1 to CM8 respectively. As you can see in Table 5, the correlation coefficients among attribute probabilities for CM1 showed a decreasing pattern from the easiest to the most difficult attributes, and the correlations were significant at the 0.01 level. 0.91 and this the correlation between A1, A4, 0.951, A1 and A5, 0.742, and so on. So this correlation coefficients show a decreasing pattern from the easiest to the most difficult attributes. Thus, the attributes in the CM1, the first cognitive model, are arranged hierarchically based on the pupil's responses. For cognitive model 2, the correlation coefficients among attribute probabilities for CM2 also showed a decreasing pattern from the easiest to the most difficult attributes, and the correlations were also significant. Therefore, the attributes in the CM2 are also arranged hierarchically based on the pupil's responses. And this is for cognitive model 3. The correlation coefficients among attribute probabilities showed a decreasing pattern from the easiest to the most difficult attributes, and the correlations are significant except the correlation coefficients between attribute probabilities for A1 and A10, 0.466, and A1 and A16, 0.508. Therefore, the attributes in the CM3 are not really arranged hierarchically based on the pupil's responses. For cognitive model 4, the correlation coefficients among attribute probabilities showed a decreasing pattern from the easiest to the most difficult attributes, and the correlations are significant. Thus, the attributes in the fourth cognitive model also arranged hierarchically based on the pupil's responses. Table 9 shows the correlation coefficients among attribute probabilities for CM5, which also showed a decreasing pattern from the easiest to the most difficult attributes, and the correlations are significant, except the correlation coefficients between attribute probabilities for A2 and A24A, 0.365, and A2 and A24B, 0.367. Thus, the attributes in the fifth cognitive model are not really arranged hierarchically based on the pupil's responses. Nevertheless, the difference between the correlation coefficients is very small, 0.002. Table 10 shows the correlation coefficients among attribute probabilities for CM6. And it showed a decreasing pattern from the easiest to the most difficult attributes, and the correlations were also significant. And therefore, the attributes in the sixth cognitive model are also arranged hierarchically based on the pupil's responses. And the seventh cognitive model also shows the same result. That is, the attributes in the cognitive model are arranged hierarchically based on the pupil's responses. And finally, as shown in Table 12, the correlation coefficients among attribute probabilities of CM8 showed a decreasing pattern from the easiest to the most difficult attributes, and the correlations were significant at the 0.01 level. Thus, the attributes in the CM8 are arranged hierarchically based on the pupil's responses. Thus, based on the decreasing pattern of the mean attribute probability for each attribute, and or the decreasing pattern of the correlation coefficients among attribute probabilities, the attributes in 7 out of the 8 cognitive models are arranged hierarchically except CM3. This indicates that we can do another revision of the CA items following the 5 steps, as I mentioned just now. Therefore, the second objective of the study to determine whether the attributes in the expert-based cognitive models are arranged hierarchically based on pupils' responses had been achieved. Finally, the Hierarchical Consistency Index, or HCI, was used to determine the consistency of model data fit between the expert-based cognitive models and the pupil-based cognitive models. HCI is an index that indicates the consistency model data fit between the expert-based cognitive model, or the expected response pattern, and pupil-based cognitive model, the observed response pattern from the pupil's responses in the CDA. In other words, HCI can be used to examine the validity of the attribute hierarchy or the cognitive models from the pupil's perspective. And the value of HCI ranges from -1 to 1. The HCI value of -1 indicates an extreme or perfect fit of the expert-based cognitive model with the pupil-based cognitive model, whereas the HCI value of 1 indicates a perfect fit of the expert-based cognitive model with the pupil-based cognitive model. And the higher the value of HCI, closer to 1, the higher the consistency between the expert-based cognitive model with the pupil-based cognitive model. And according to Roberts et al. 2014, a HCI value less than 0.6 indicates a poor fit. A value from 0.6 to 0.8 indicates a moderate fit. And a HCI value more than 0.8 indicates an excellent fit between the expert-based cognitive model and the pupil-based cognitive model. HCI was calculated using Microsoft Excel 2016, and we hired an expert to do it for us. And table 13 shows the mean HCI value for each cognitive model. As you can see in the table, the mean HCI value for CM1, CM2, CM3, CM7, and CM8 was more than 0.80, based on indicating an excellent fit between the expert-based cognitive models and the pupil-based cognitive models. The mean HCI value for CM4, 5, and 6 was from 0.60 to 0.80, indicating a moderate fit between the expert-based cognitive models and the pupil-based cognitive models. Thus, the last objective of the study to determine the consistency between the expert-based cognitive models and the pupil-based cognitive models has been achieved. An example of score profile. The example of score profile is based on a cognitive model that measures the concept of a calendar date involving finding duration between two inclusive dates from another study, not this study, but under the same research project. So a sample item in this cognitive model, this is the practical side of CDA, the practical use of CDA, the score profile. So a sample item in this study, another study, Siu Hong went to her aunt's house on 3rd June 2014. She stayed until 2nd August 2014. How many days did Siu Hong stay with her aunt? To solve the item, the pupil needs to understand the concept of inclusive dates. That is to include both 3rd June 2014 and 2nd August 2014 in calculating the duration. Thus, it gives a duration of 61 days instead of 60 days. That is 3rd June to 30 June, 28 days, 1st July to 31st July, 31 days, 1st August to 2nd August, 2 days. So the total is 61 days. So in this cognitive model, there are 18 items measuring 6 attributes, A1.0 until A.35. So figure 3 shows a description of the attributes and hierarchical structure of this cognitive model. As shown in this figure, attribute A1 is the most basic attribute, which is the prerequisite for all the cognitive attributes in the cognitive model. And pupils are expected to master the attributes from the easiest to the most difficult in the cognitive model. For example, attribute A1.0 is a prerequisite for attribute A3.1, while A.1 and A3.1 are prerequisites for A3.2, and so on. In the sample item, which asks about Siu Hong's stay, tested all the above attributes from A.1 to A3.5. So a pupil is expected to master all these 6 attributes before he or she can solve this item correctly. And if a pupil fails to answer this item correctly, then we could diagnose which attribute that these people had not yet mastered based on the generated knowledge state. To diagnose the pupil's mastery level for each attribute measured, the knowledge state is generated, and the knowledge state was obtained from interpreting the attribute probability calculated by the Artificial Neural Network, or ANN, in MATLAB 2012. Table 2 displays an example of an array of knowledge states of a sample of 19 pupils generated by ANN for the above cognitive model. As mentioned earlier, there are 6 attributes, A1, A1.0 to A3.5 attributes. Each attribute is measured by 3 items to increase the reliability of the CDA. Therefore, there are 18 items altogether, 6 times 3, 18 items. So the first column indicates the identity number of pupils, while the last column shows the knowledge state of the individual pupil, and the middle 18 columns show the observed response patterns of the 18 items. And all responses were converted to binary pattern, with 1 indicating a correct response, while 0 indicating an incorrect response for the calculation of the attribute probability using ANN. As shown in table 2, pupils who answered only the first 3 items correctly, that is FCK 002, 009, 012, and 017, had shown mastery in the first attribute, A1.0, measured by items 1 to 3, the first 3 items. And non-mastery in the rest of the attributes, non-mastery, all zeros, right? And in the rest, and the knowledge state was represented as 1, 0, 0, 0, 0, indicating that they only mastered the first attribute, and the last 5 attributes they didn't master. Interestingly, pupil FCK010, this pupil, failed to answer all the first 3 items, 0, 0, 0, at the first level of the hierarchy, but answered correctly 1 item at the second level and 3 items at the third level of the hierarchy. Through the calculation of ANN, these pupils showed mastery of the first attribute, inconsistent mastery of the second attribute, but non-mastery of the rest of the attributes, and the knowledge state was represented as 1/2, 0, 0, 0, 0. The results seem so, as pupils were expected to master the easiest attribute before they can master the more difficult attributes, as predicted by AHM. Hence, when pupil FCK010 could answer items at the third level of the hierarchy, he was expected to master the first attribute. And to determine the pupil's attribute mastery level, a cutoff value of attribute probability was used. And this is based on the acceptable standard and the standard of excellence used by Alberta Education according to ELF 2011. And table 3 shows the classification and interpretation of the attribute mastery level. As you can see, the attribute probability value of more than 0.8 was represented by a value of 1 in the knowledge state, which was classified as mastery of the attribute and was reported as an in-depth understanding of the attribute in the score profile. Whereas the attribute probability value from 0.5 to 0.8 was represented by a value of 1/2 in the knowledge state, which was classified as inconsistent mastery and was reported as incomplete understanding of the attribute in the score profile. And finally, the attribute probability value of less than 0.5 was represented by a value of 0 in the knowledge state, which was classified as non-mastery and was reported as insufficient understanding of the attribute in the score profile. To illustrate further, figures 4A, 4B, and 4C are extracted from table 2. The knowledge states of 3 pupils with different levels of performance, high, average, and low, are selected as examples. As shown in the table, the first row shows the pupils' responses, this row, for the 18 items, whereby each attribute was measured by 3 items. A score of 1 was given for a correct response, while a score of 0 was given for an incorrect response. And this set of responses was analyzed by using ANN to obtain the attribute probability. And based on the attribute probability, knowledge state, as shown in row 3, was determined based on the cutoff values in table 3 that I explained just now. And finally, the pupil's attribute mastery level of each attribute, as shown in the last row, was determined according to their knowledge state. So in other words, their attribute mastery has reflected the pupil's knowledge state inwards. So figure 4 shows a high performing pupil who had answered 16 of the 18 items correctly. Therefore, the pupil was given a score of 1 for the 16 items. And this set of responses was analyzed by using ANN to obtain the attribute probability ranging from 0.96 to 1, as shown in row 2. Then, based on the attribute probability, the knowledge state of this pupil was represented by 1, 1, 1, 1, 1, 1 for the measured attributes, as shown in the third row. And this knowledge state indicated that the pupil had shown mastery of all the measured attributes for this high achieving pupil. And this figure shows an average performing pupil who had answered 12 of the 18 items correctly. Therefore, the pupil was given a score of 1 for the 12 items. And this set of responses was analyzed by using ANN to obtain the attribute probability ranging from 0 to 1, as shown in the second row. And based on the attribute probability, the knowledge state of this pupil was represented by 1, 1, 1, 0, 0, 0 for the measured attributes, as shown in the third row. And finally, this knowledge state indicated that the average performing pupil had shown mastery of the first 3 attributes, but non-mastery of the last 3 attributes. Finally, figure 4C shows a low performing pupil who had only answered 3 of the 18 items correctly. Hence, the pupil was given a score of 1 for the 3 items. And this set of responses were analyzed by using ANN to obtain the attribute probability ranging from 0 to 1, as shown in the second row. And then based on the attribute probability, the knowledge state of this pupil was represented by 1 and the rest zeros for the measured attributes. And this knowledge state indicated that the low-performing pupil had shown mastery of the first attribute, but non-mastery of all the last 5 attributes. In brief, by looking at the score profile of each pupil, as shown in the 3 figures above, the teacher can determine which attribute the pupil has not yet mastered, even to the detail of which item the pupil has not answered correctly. Based on this fine-grained information, an appropriate remedial instruction can be planned by the teacher to help the pupil to overcome his or her weaknesses. CDA, so in conclusion, CDA is useful for diagnosing pupils' learning progress because it provides fine-grained feedback to both teachers and pupils. And by using A and N to determine the attribute probabilities, the knowledge state can be generated for each pupil. And this knowledge state shows the pupil's attribute mastery level for each measured attribute. And this fine-grained information serves several functions to both teachers and pupils. First, through CDA, teachers will know if their pupils have fully understood the whole topic or subtopics and knowing which parts to reteach before moving on. And by knowing pupils' attribute mastery level, it will aid in their instructional planning for future lessons. And second, based on the score profile, the pupils can monitor their own learning progress over a period of time. This is because the score profile shows clearly to what extent they have achieved and how far they are from their learning goals. And third, through observing the pupils' response pattern, teachers can have an overview of the types of errors and the common errors committed by their pupils. In addition, all items in the CDA were designed based on the cognitive models, and each attribute was measured by 3 parallel items. Therefore, the teacher could collect enough evidence of pupils' misconceptions or systemic errors in learning, which can help their remedial instruction. And fourth, teachers may use flexible grouping as a strategy of differentiated teaching method to group pupils with the same or similar knowledge state together. And this way of grouping helps the teacher to carry out the remedial instruction to the targeted group of pupils more effectively. However, there are 3 main limitations during the development of the CDA in this study. First, the process of developing a CDA was time-consuming and thus less practical for teachers. The development of CDA could not be carried out by a teacher alone. Instead, it needs a panel of experts, experienced and committed teachers to contribute their ideas in different steps of the development and evaluation of the CDA, especially in identifying the attributes, development of the expert-based cognitive models, and designing the CDA items. And in fact, the development of the cognitive models and revising them was the most challenging and time-consuming step. This is because the panel of experts must constantly brainstorm and discuss in detail to ensure that each attribute was clearly defined and arranged in the correct attribute hierarchy. Second, the data analysis required the use of psychometric procedures such as HCI and attribute probability. And many teachers might not be familiar with the psychometric procedures and ANN in MATLAB 2012. They might need the assistance of experts in this matter, like the researchers in this study. We need the assistance of experts in ANN and HCI. Third, as the developed CDA was administered and scored manually, it was not possible to produce pupils' knowledge states or score profile immediately. This delay in reporting may cause the diagnosed pupils' knowledge states become inaccurate or invalid in making inferences about a pupil's current knowledge states. This is because pupils' knowledge states are dynamic and change constantly and only valid at the point of measurement. Nevertheless, the latter issue may be addressed by developing a computerized or online system for the CDA. Therefore, an online CDA is recommended for future study. Online CDA will not only be easier to be accessed by both teachers and pupils, but also enable the score profile to be produced almost immediately after the assessment has been taken by the pupils. And with this, thank you very much for your attention and patience. And excuse me for going too fast because I thought I was given 2 hours to deliver my lecture, but according to Dr. Dina, I was given 1 hour. So I had to rush. Sorry for okay, thank you. Thank you very much.
Okay, thank you very much for a very interesting presentations, Dr. Chu. Yeah, 2 hours, but including all sessions. I'm terribly sorry for not informing you that from the very
But it's
beginning.
okay. I have my lecture afterwards, so it's okay.
But firstly, allow me to give a kinds of short recaps in Bahasa Indonesia to
Okay.
the participants. Bapak Ibu sedikit mungkin ya berbagi catatan kecil ya terkait presentasi yang sudah dipaparkan oleh Dr. Cheng. CDA, actually, I am very familiar with the term CDA, but my field of expertise is in language. In language, we also the term.
Oh, I see. That's very good.
It refers to critical discourse analysis, not cognitive diagnostic assessment.
Wow.
So
I will
they both
invite you for the visiting scholar. Because I'm not mistaken, we had a MOA between your university and USM in 2018 when Dr. Hepsi came to USM, right? I think it's active until, I think it's a 5-year MOA, right? Or 3-year, I can't remember.
Yeah, it's in the process of extension, actually. Yeah.
Good.
We are about to send the MLU for the extensions this month. Okay.
Thank you.
Ya. Oke, kembali lagi ya Bapak Ibu. Jadi CDA itu merupakan assessment atau didesain untuk mengukur struktur keilmuan yang spesifik dan kemampuan siswa untuk menyediakan informasi terkait kekuatan dan kekurangan kognitif siswa. Ada beberapa background atau alasan dalam melakukan penelitian yang dilakukan. Pertama, karena tes dan ujian tidak ramah bagi proses pembelajaran, tidak ramah bagi kurikulum, tidak ramah guru juga, dan tidak ramah siswa. Hasil dari Cognitive Diagnostic Assessment dipresentasikan dalam bentuk knowledge state. Saya kurang tahu juga nih ya dalam bahasa Indonesia padanannya apa ya, yang menyediakan informasi tentang penguasaan siswa terhadap proses terhadap pengetahuan atau kemampuan yang diperlukan untuk dapat menyelesaikan masalah atau tugas yang diberikan, gitu ya. Mungkin Bapak Ibu juga bertanya apa sih yang dimaksud dengan atribut tadi ya yang dipaparkan. Atribut adalah pengetahuan atau kemampuan ya yang diperlukan untuk dapat menyesuaikan atau menyelesaikan permasalahan atau tugas yang diberikan guru di dalam pembelajaran. Okay, so far we have one questions in the chat box, Dr. Chu. Okay, it's from M. Roshad. Okay, the first question is, after doing CDA, how about motivations for the students learning doing mathematics? So that's the first question. And the second question, so he asked about probably the significance or the relations of motivations and students.
Yes. Okay. Amrose study. Okay. How about motivation for the students learning doing mathematics?
Yeah.
This is not the objectives of our research, but with the knowledge, with the score profile generated from CDA, the students will know his or her cognitive strengths and weaknesses in the topic tested. So based on the weaknesses, the teacher can help the pupil to have a remedial instruction to guide the students to improve on the weaknesses identified in the score profile. So I think if the students can master these attributes after the remedial instruction, then it will act as a motivation for the students to keep on learning later. Did I answer the question?
Yeah, correctly. So after knowing the profile or the result, from the test, so it can be a stimulus or a stimulant for the students, to.
Yeah, it will be better if the teacher provide a remedial instruction based on the score profile.
Okay, that's good. Okay, the second question from Roshadi is, based on your presentations, what can be measured from the result of CDA assessment for students related to mathematical ability?
Where is it?
Still, because there are two questions posted by...
I see. What is the second question?
This one, based on your presentation, what can be measured from the result of the CDA assessment? CDA.
It's actually the score profile, the knowledge state in the topic that you are assessing. So the score profile will show the mastery and non-mastery of the attributes in the topic measured by the CDA. So in my research, the topic is time. So all the attributes in learning the topic of time will be assessed in my CDA. So the results, the score profile of the CDA will indicate which attributes have been mastered or not mastered or mastered inconsistently by the pupils. So these are the results of the CDA. It shows the mastery and non-mastery level of the attributes in the topic measured.
Okay, so the measurement will be based on the topic, yeah.
Yes. You can't do for all topics, definitely, especially in a research project.
So it's very specific.
It'll be good. Yeah, it must be very specific because the result should be very fine-grained, very specific. In fact, there are 4 properties of attributes. Number 1, it must be measurable. Number 2, it must be fine-grained. Number 3, it must be relevant to your learning outcomes of the school curriculum.
Thank you very much. Okay, the second, probably we will get to.
I think one more question, Dr. Dina. Asking about using ANN-MATLAB to determine, okay, what if I want to calculate manually or calculate with Microsoft Excel? Yes, because that time, this project was not my project. I was just a co-researcher. So we hired a graduate research assistant to do all the calculations. So the graduate research assistant used MATLAB to calculate ANN, to calculate attribute probability using artificial neural network, and using Microsoft Excel to calculate HCI. So my recent project, doing the online CDA, yes, my GRA used Microsoft Excel. She programmed the formula into Microsoft Excel to calculate HCI, but ANN, now she used, you don't have to use MATLAB. Microsoft Excel, I'm not very sure, but my GRA used SPSS, the latest version 27. Now it has the ANN features, so you can try this. So now SPSS can calculate ANN. You have to train the ANN to come up with the attribute probability.
Bisa pakai SPSS ya, Ibu.
Yes, SPSS can calculate ANN. So not necessarily MATLAB, but Microsoft Excel, I don't think so, because you need a very special software to train it to produce the expected, to produce the observed, the expected response patterns and based on the observed response patterns.
Okay, before going to the next questions from the chat box, Padori Setiawan is raising his hand. Padori, would you like to ask questions directly to Dr. Chu?
I think got one more question, Dr. Gina.
Yeah, okay. Yeah, from Christiana.
Harapan Bangsa Junior High School.
Yeah.
And she asked about currently which country starts on developing CDA online. I think many countries have started online CDA, including Australia, New Zealand, US, and lately Malaysia. I started online CDA, and it's still ongoing. Therefore, I cannot present it here because of copyright issues with USM. But I'm going to present the pilot findings in the ICME conference next month. You know, ICME, International Conference on Mathematical Education, in Shanghai online. So if you participate, I think there are 2 Indonesian lecturers, invited lecturers. To currently, one more, I can't remember. There were 2 lecturers from Indonesia presenting at ICME 14. So there are many countries now doing online CDA. And it is similar to analysis butir soal Indonesia, but the program will be presented in narrative. I'm not very sure what did you mean here, analysis butir.
Okay, or Bu Christina, can you clarify? Can you unmute yourself?
Okay, so Indonesian term. Is it item analysis?
Yes, item analysis.
That means you are referring to the item difficulty index, item discrimination index, right?
Yes, after we are giving an assessment to our pupils, and then the result will be developed by the program directly, like how many difficult question, medium, and
yes. So I understand. Yes, to develop an assessment, definitely.
Only on the quantitative, I think.
So this we call item analysis. Definitely, when you develop assessment, you need to do item analysis. That is the item difficulty index and item discrimination index. For CDA, you need to do the psychometric analysis using HCI to prove that the expert-based cognitive models, that means the expected response patterns, you predict the observed response patterns from the pupils. So in our study, we did calculate the item discrimination index and the item difficulty index, and the p-value shows that most of the items are of moderately difficult, also good discriminating items, except the most basic items, the easiest attribute. They have a very low difficulty and also low discrimination index. That's all. So we did, but I didn't report it here because I focused on CDA. So for any assessment, definitely you have to calculate item difficulty index, the p-value, and also the item discrimination index, or DI, or some people use the point by serial correlation coefficient, RPB.
Mr.
Yeah, okay.
Bu Heni Hasibuan.
Okay. You tell me about that item difficulty index, right? So how about the item difficulty index? Are you just focused on an easy question?
No. Based on the item difficulty index results, so the easy items, if most of the items are easy, then you have to revise or remove the items and come up with new items. So ours, most of the items were of moderate difficulty. So we didn't do any revision and we maintain the items.
So there are no difficult questions, right?
Yes, we have, especially the highest attribute, the most difficult attribute, the word problems. We have high difficulty index.
Is it okay for the diagnostic assessment, the difficult questions?
Yes, definitely. Only 10% of our items.
Oh, okay. Thank you.
Yeah. Yes, any more questions?
Okay. Any more questions from the participants? Paduri Setiawan, would you like to ask questions?
Any docent from Universiti Malang, because I visited Malang.
Okay, anyone from Malang? Ada yang dari Malang katanya? Universitas Negeri Malang?
For the international teaching practicum, I went to Malang to observe my students. We exchange students for teaching.
Oh, you visited Malang?
Yeah, I remember.
Yeah, because based on our registry, there are lectures from Universitas Negeri Malang. Ibu Bapak ada dari sini yang dari Malang? Nobody, I guess.
May I know how many universities participating in this webinar, Dr.
Yeah,
Zina?
according to the registrations, there are more than 5 coming from different universities, but based on the numbers, actually there is supposed to be 200, but here there are only 130 participants, so more than 70 participants are not attending. For me, who are not in the math field, so I'm not quite familiar with all the things, but it's very interesting. But I have a questions, or I was thinking then, actually, what is that? A very basic questions. The significance of doing CDA, especially related to the teacher's classroom instructional practices. If at the end, the teachers, or after getting the profile of the student, then the teacher can give remedial, or can, let's say, fix something in his or her instructional practices. But from in the very beginning, so what is it for, Dr. Cheng?
Yeah, to make
the profile?
To make the assessments more friendly in terms of the 4 aspects, teacher and so on, right? But with these manual CDA, paper pencil test CDA, there are limitations. So that's why I propose doing online CDA, and that will be very helpful to teachers, because you can get the score profile immediately, and you can plan for remedial instruction during the next lesson. So this will definitely help the teachers to improve the students' cognitive strengths and weaknesses.
Well, we need panel of experts, as you said earlier, right?
Yeah.
So it's time consuming, and seems to be
the panel experts were used to develop the cognitive expert-based cognitive models.
Only the models.
I think I saw one question here. Item response theory. Yes, item analysis is based on IRT, item response theory. And now I think some are using rush model to analyze the items. But for my CDA, I just use the psychometric procedures as recommended in the literature.
Can we do this type of tests nationally?
My project is such a small scale project. I'm not very sure. But I hope it will be. That will be very good.
Yeah, because we have national exam to measure all the students, right? Best competence in math, for example.
And it definitely helps in a school-based assessment. Because Malaysia implemented school-based assessment because of the weaknesses in the traditional tests and examinations in 2011. But they just report in terms of broad bands, band 1 to band 6, not the fine-grained details like the score profile.
Okay.
So that's why we propose using CDA.
CDA. Okay. Very interesting. Okay. Other questions? Any questions from the participants? Or Dr. Chu can elaborate more, or give us descriptions about the students' competence, especially in the field of mathematics in Malaysia, so that we know, can have a little bit, highlights about math, students' competence in Malaysia related to math.
I think these competence are reported in TAMES and PISA, right? And Malaysia, of course, still not the top 10 ranked countries in the world, but it's improving, slowly picking up. In the latest teams is improving. So that I think should be the benchmark of Malaysian students' competencies, especially for grade 8 students. We didn't take part in grade 4, but we took part in grade 8. It's secondary school in Malaysia. I think I have to share one more, the Q matrix. That one I didn't share with the participants because we have time, right?
Yeah, we still have time.
Because when we develop CDA based on the expert-based cognitive model, we have to come out, we have to generate 4 matrices. The A matrix, the R matrix, Q matrix, and the QR matrix. So since we have time, I'll just share with you. With the participants, the matrices. Okay, so wait. Can you see my slide? Oh,
not yet.
Not yet, where is it? Yeah.
Okay.
Okay, can you see now?
Yeah.
All right, good. So this is okay. So this is done during step 2, development of expert-based cognitive models at the step 2. So this step began with generating the pure matrices, which serve as the attribute blueprint for the development of CDA items. And there are 4 sequential matrices developed based on the attribute hierarchy or the cognitive model, namely the adjacency, the reachability, incidence, and reduced Q matrices. Adjacency is the A matrix, reachability is the R matrix, incidence is the Q matrix, and reduced Q matrix is the QR matrix. So the reduced Q matrix represents the expected response pattern based on the expert-based cognitive models. So we use this to predict the students' observed response patterns. And it's also known as the expert-based cognitive model in this research. So the A matrix is a K by K order binary square matrix. K refers to the number of attributes in the cognitive model, and which is used to represent the direct prerequisite relationship of the attributes in CDA. And it was derived from the attribute hierarchy by positioning the value 1 or 0, 2 values, and the respective entry of the A matrix to indicate the presence or absence of a direct prerequisite relationship. The keyword is direct prerequisite relationship. Presence or absence. Presence, we use 1, absence, we use 0 between the attribute pair. So this is the example, the process of deriving the A matrix is shown in figure 5. So as shown in figure 5, the value 1 is positioned at row 1, column 2, this one. because A1 is the direct prerequisite attribute for A2, as you can see here, the sample cognitive model. A1 is the direct prerequisite of attribute A2. A2 is the direct prerequisite attribute of A3. A1 is direct prerequisite for A3. So this value 1 is positioned here to show the direct prerequisite attribute for A2. All right. And the value 1 is positioned at row 2, column 3, this 1, because A2 is the direct prerequisite or attribute for A3. So I repeat, A1 is the direct prerequisite for A2. A2 is direct prerequisite for A3. So it's represented by the value 1. Whereas 0, no direct prerequisite attribute based on this cognitive model. So the value 0 is positioned at row 1, column 3, because A1 is not the direct prerequisite attribute for A3. All right, so this is the A matrix showing the absence, the presence or absence of direct prerequisite attribute represented by 1s and 0s. Then another K by K order binary square matrix named R matrix is derived to represent the direct and indirect relationships between the attributes in CDA. So R matrix can be derived from A matrix by performing Boolean addition and multiplication. And we have to use the formula R equals A plus I to the power n. A represents the A matrix, I represents the identity matrix. When I refers to identity matrix and n refers to the integer required to reach invariance. To reach invariance means we get the same matrix R after substituting the value of n. So the definition of Boolean addition and multiplication is as shown below. We follow Tatsoka 2009. You can refer to his article. So for Boolean addition, 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 1 equals 1. And Boolean multiplication, 0 times 0 is 0, 0 times 1 equals 0, and 1 times 1 equals 1. So we use this when you multiply, when you add or multiply the two matrices. So this is the diagram, figure 6. R matrix is obtained if the value of R remains the same, invariant, when the integer n is substituted with two subsequent integers. The value of n must be subsequent. All right, so for this example, R matrix was derived as shown in this figure. The value of R remains the same when the integer n substituted with 2 and 3, as shown in the figure. Can you see when n is 2, you get this matrix R, and when n equals to 3, you get the same matrix R. So R has reached invariant, the same. So therefore, we have found the R matrix. And to get when you substitute n equals 1, you have to use this formula A plus I power n. So A plus I, take matrix A plus matrix I to power 1, and you have to use the Boolean addition and multiplication rules, and then you obtain this matrix R. So when n equals to 2, then you use the A plus I, which is this matrix. Square means you times this matrix again, you'll get this. So you have to do the multiplication by yourself. And then when n equals to 3, you take A plus I squared times A plus I, you'll get this result. So from substituting n equals to 2 and n equals to 3, we get the same R, and therefore this is the R matrix. A1, A2, A3, A1, A3, measuring attributes. So the value of 1 or 0 in the R matrix indicates the presence or absence of the direct, indirect relationships between the attributes. So matrix R show direct and indirect. Whereas A matrix shows the absence or presence of direct relationship. So based on the R matrix, the second value of 1 in the first row indicates that A1 is the direct prerequisite attribute for A2, while the third value of 1 indicates that A1 is the indirect prerequisite attribute for A3. And in the second row, the third value of 1 indicates that A2 is direct prerequisite attribute for A3, but not A1. And remember, according to Tatsoka, all the diagonal positions of R matrix here are occupied with the value 1. And this does not indicate that A1, A2, and A3 are the prerequisite attribute for themselves. However, this implies that each attribute is reachable from itself. That means 0 step is required. Next, after the R matrix, we generate the Q matrix. The binary Q matrix with order K times I. K is the number of attributes, and I is the number of potential items. Remember, you want to develop items, so we must know the number of potential items based on the cognitive models. So was derived to illustrate the involvement of the attributes. The Q matrix shows the involvement of the attributes in each item on the potential item pool. So the number of potential items can be determined by using the formula I equals to K minus 1, where K is the number of attributes, right? So since there are 3 attributes in the expert-based cognitive model, in this example, so based on the formula, the number of potential items is 7. That means you substitute here, I equals 2 power 3 minus 1, 8 minus 1 is 7. So we know we have potential items 7, the number of potential items. And the Q matrix now is of 3 times 7 order. 3 attributes, 7 potential items. So the attributes involved in each item was determined based on set theory. Set B is defined as a set of attributes in cognitive model 1. That is, B is a set of consisting of 3 elements, A1, A2, A3, the 3 attributes. Since there are 3 attributes in the cognitive model, a total of 8 subsets can be formed, set theory. So the number of subsets is 2 power n, where n is the number of elements in the set. So the 8 subsets of set B are set A1, set A2, A3, A1, A2, A2, A3, A1, A3, and all the attributes A1, A2, A3, and empty set, no attribute. So we have 8 subsets. And so the process of getting the Q matrix is shown in figure 7. So except for the empty set, each subset illustrates the attributes involved in the Q matrix. So you can see here, the first subset A1, item 1, represented by Q1. So Q1 you involve attribute A1, A2, Q2, A3, Q3, and Q4, item 4, will involve 2 attributes, A1, A2, based on the subsets. Item Q5, A2, A3, item Q6, A1, A3, item 7 involve all the 3 attributes, and empty set, no attributes, so no item. All right, so we have 7 potential items. So based on the attributes listed in each subset, the value of 1 or 0 could be positioned at the row entry for each column in the Q matrix, as example here, right? Indicate the involvement of the attributes in the item. So based on the subset A1, for example, subset A1, item Q1, right? So this column, the value 1 is positioned in row 1, but the value 0 is positioned in row 2 and row 3. Because the first column Q1 represents the item that only involve A1 only. So in short, Q1, item Q1 involve only the first attribute. Item Q2 involve the second attribute. Q3 involve the third attribute. Q4 involve attribute A1, A2, A1, A2, A3, A1, A3, and A1, A2, A3. So this is the Q matrix representing the potential pool of items. There are 7 potential items to be generated based on this cognitive model. And after that, the Q matrix was reduced because of overlapping items. So reduced to form the QR matrix. QR means reduced Q matrix. That means the number of potential items have been reduced to the essential items based on the inclusion relationship. After I've shown you that satisfy the attribute hierarchy as shown in the cognitive model. So these items are identified from the potential item pool represented by Q matrix by imposing the direct and indirect prerequisite relations of the attributes specified in the R matrix. So for this example, A1, and this implies that items are constructed. I think I can skip this. This is an important one. A1 is involved in all items, right? Because this is the most basic attribute. A2 is involved in the items measured in A2, and A3 is only involved in items measured in A3. So this is the inclusion relation. A1 is a subset of A2, A2 is a subset of A3, all right? So based on this, as you can see, the item measured in A2 would involve the prerequisite attribute A1. This is the Q matrix, the potential pool of items, but we know from the inclusion relationship, Q2 must involve attribute A1, right? Because A1 is the prerequisite attribute for A2. So therefore, this column 010 does not follow this inclusion relation, but it is equivalent to item Q4 110. A1 involve A1 and A2. So item Q2 will be removed and replaced by item Q4 because it can measure attribute A1 and A2, right? And similarly for Q3, 001, it does not follow the inclusion relationship. It should include A1, A2, and A3. And it is equivalent to item Q7, which involve all the three attributes. Likewise, Q5 only measure A2 and A3, and Q6, A1, and A3 should include A1 and A2, and they are equivalent to Q7. In other words, only item Q1, Q4, and Q7 will remain after removing the three items that do not follow the inclusion relationship. So finally, the Q matrix, the potential pool, will be reduced to this QR matrix. That means item Q1 measure attribute A1, Q4 measure attribute A1 and A2, Q7 measure all the attributes. And this follows the inclusion relationship because this is based on AHM, attribute hierarchy method. All right. So this is the items, the number of items that you need to develop in your CDA for this cognitive model. And in order to increase the reliability of the CDA, remember, we can use three parallel items measuring one item. So we can expand this QR matrix, become expanded version of QR matrix. So Q1, you have another two items. So you have Q1, Q2, Q3, and measuring the same attribute, 100, 100, 100. And likewise, Q4, Q7 have another three items. So we can expand it to include 9 items in your CDA. I think that's all. Okay.
Okay.
Yeah.
Thank you, Dr. Chu, for additional
okay.
presentation.
Yeah, almost fine. Okay.
Yeah. Actually, we have two more questions in the chat box from Ibu Hani Hasibuan. Okay, you said a teacher could arrange remedial lessons from the students' performance in CDA. Is it just for non-mastery or inconsistency mastery?
I think should be both. The inconsistent mastery, because the student might not master the 3 parallel items. It could be 2 out of 3 or 1 out of 3. So that's why it's inconsistent, incomplete understanding. So it should be planned for this student.
The CDA provide...
you can group the students according to their knowledge state. And it's easier for the teacher to plan their instruction to the targeted group having the same knowledge.
Okay. Does CDA provide an overview of students' profiles or just focused on each attribute?
Yeah, in fact, it can be, the score profile is for every individual pupil. What I reported is the mean is for the group, because you want to find the overall consistency between the expert-based and pupil-based cognitive rules. So it's possible, especially if it's online, it can show the score profile for each student for each cognitive model in detail.
Okay. One more question from Rudy Salam. Is CDA appropriate for both formative and behavioral concept?
Again, pardon?
Is CDA appropriate for both formative design concept and behavioral concept? I don't know, Pak Rudy, can you please clarify your questions? You can unmute yourself and ask the questions directly to Dr. Chu.
It's more appropriate for formative because it's so fine-grained, very specific, very particular topic. Behavioral, I'm not very sure because now what I'm focusing is on the cognitive, not the behavioral, not the psychomotor aspect.
Okay, thank you very much for the clarifications.
Right.
Answer. Okay, any questions from the participants? We still have around 10 minutes to the end of our sessions. No questions? Oh, Bu Ida, Farida? Oh, no. Okay, to probably Dr. Chu can give a concluding remarks, or a closing remark from the presentations.
In fact, I've already made the conclusion at the end of my presentation. I reported the limitations of my study, and I proposed the online cognitive diagnostic assessment. And it's not only for mathematics; it can be applied, I think, to all subjects, especially like English language. I think I found quite a few in the literature on English language, and mathematics, not so many. So focusing on time is even very limited, mostly on algebra, etc. Right? And mostly at the primary school level. And we have the retrofitting CDA. That means they use what do you call that, the national examinations or even international assessment like PISA teams. Then they retrofit into the CDA. That means they choose the items from the teams and PISA, and then they develop their CDA. So there are two ways of developing CDA.
Okay, if there's no more questions from the participants, I guess we come to the end of our sessions. Thank you very much, Dr. Chu.
Thank you very much.
Did I pronounce your name correctly? I'm afraid.
Yeah, I'm Chu. Chu Cheng Meng. Okay.
We have, Buhani has it's a request actually. Can you show us the output of the students' performance in doing CDA?
Again?
Can you show us the output? Is it the result, Ibu Hani, of the students' performance in doing CDA? The result of the test, is that what you mean, Ibu Hani Hasibuan?
You mean the answer scripts?
Can you show us the output of the students' performance in doing CDA?
Yeah, so I think it means the answer scripts, right?
Yeah.
Unluckily, I'm not the main researcher of this project. The main researcher was Professor Dr. Lim Chap Sam, and she had passed away last year, and she didn't pass the data to me, so I do not have the answer scripts. I just, for this lecture, I just based on the articles written by Professor Dr. Lim and her students, published in book chapters and also international journals. You can find these articles, I think. One was published in IJSME, International Journal of Science and Mathematics Education, and one in Malaysian Journal of Learning and Instruction, and one in USM book as a book chapter, right? So I'm very sorry, I do not have the answer scripts of the students.
Okay. So we come to the end of our sessions, Dr. Chu. So as the
okay, can you email this certificate to me?
Yeah, sure, we will. Yeah, we will. So we are, as a token of appreciations for being the speakers of our today's event. So we are going to send, this is the digital, but we will send you the
very important
to your email. Okay. And Udi is also sending a warm regards to you. Sorry for not being able to attend.
No problem.
Okay, so then to conclude or to close, actually, to close our sessions, let me take some quotes, actually. So assessment makes teaching into teaching. Mere presentation without assessments of what the learners have made or what you have offered them in the teaching learning process, then it's not teaching. So assessment is a very integral part of learning process. Okay, I guess that's all for today. So let's close our session for today. So I'll see you in the next webinar. Good afternoon, everyone. So thank you very much, Dr. Chu.
Thank you very much, everyone. Thank you very much.
Okay.
Thank you, Mr. Chang.
All right. Can you send the recording of this webinar to me also?
Okay, we will.
Okay,
we will.
All right.
Okay, thank you very much, Dr. Chu.
Thank you. Welcome.
Okay,
bye.
Bye.
I shall leave now. Thank you.
You can leave.